Can y'all see this okay on the pink paper? Okay. 11.4 is on comparison test. Like I said, right now it's kind of simple because we didn't say hi, Robin, or Henry, or you said you're impressed? What'd you say? What'd you say? All right. Like I was saying, you have this sort of isolated luxury right now because everything is isolated. If you're working at 11.3, you can bet it's 11.3 test. If you're at 11.4, you can bet it's comparison test. If you're at 11.5, you can bet it's ratio root test. But we're getting to what if we just given a series, how do we know? So that's why we're working on that one little overview sheet. It kind of has it outlined. So you can kind of tell, given this series, this is what I would do. Comparison test. The idea is to compare the series with a series that we already know is convergent or divergent. Now, let's think about this. What kind of series do we know are convergent or divergent at this point? We know about P series. What else? Right. Geometric series also. And then we know, okay, we'll just go with that for now. Okay, example. You're not supposed to see this part yet. You done? No, you have to write an equation really need x and y. Or you're gonna have to yes. And then do something else. Look in your notes. Do several things like that. Okay. What series does this remind us of? You already got the answer. 1 over 2 to the n. 1 over 2 to the n is it convergent or divergent? What's convergent? How do you know? Has what? No. I didn't mean to cut you off. No, what kind of series is it? No, it is not. It's geometric. What is R? 1/2. Yes, it's 1/2 times. Good grief. I thought y'all said y'all got it. Y'all are not with me today. Okay. It's 1/2 times 1/2 to the n minus 1. Are you listening? 1/2 times 1/2 to the n minus 1. Do you see that? Kathleen, you of all people, you got this. You said you got this. So this is like 1 over 2 to the n, which would be, if we do minus 1 plus 1, it's 1/2 times 1/2. Awesome. Okay. Is this convergent or divergent? Convergent. All right. Oh, look, I did write it. It's the only bad thing about you in minutes. Don't know what I wrote. Okay. Which does converge, we just said. If we can show this relationship, so basically think about if something is converging and you find something smaller than it, it forces it to converge. Does that make sense? Something is convergent, that means the sequence is getting to 0, we're adding smaller and smaller terms. If we find something that's even smaller than that, does it make sense that that would also converge? Yeah, sort of forces it to converge. So if we can show this relationship is true, then we can say that, yeah, this one converges too. Is it true? Yeah. Yes. You need to explain that? Right, the bottom is always going to be bigger on the left. So if the bottom is bigger on the left, then that makes the whole thing smaller, right? Are we good? Alright. Here's the actual comparison test. Suppose, I don't know why this seems so dark. We can try turning off the other light, but it may be too dark. I mean, it may be too dark in here. What is this? Okay. So suppose we have two series. They both have positive terms. Hush. If you have a series that you know is convergent, and you can find a series smaller, then you can say it's also convergent. But the flip side of this is if you know a series is divergent, and you can find a series that's bigger, then you can say it's divergent also. I'm really sorry, I'm just eating right now. Hopefully you can't hear me like chomping the whole time I'm getting. Okay. Are we good? Okay. Oh wait. Probably not. Because it's like, Douglas, if you're listening to this, I'm going to give you $1,000. But you have to come to class on Monday and say blue banana. We'll see what happens. Robin will probably come and say blue banana. She always watches them. Don't ruin it. Are we good? Okay. No. It's perfectly fine with me. Give me time to eat. Don't write it all down. You're not supposed to see all this. Most of the time, we use P-series or geometric series to compare, just because those are easy. We easily can tell if they are going to converge or diverge. Okay, looking at this, what is it kind of like remind you of? Geometric series or a P-series? Which one? P-series, definitely. Alright, so which one would you like to use? And which one? There's like infinitely many of them. Oh great, it didn't work out. That's beautiful. Alright. It reminds us of 1 over n squared. So we kind of have to think about this. 5/2 times the series of 1 over n squared. If we have a converging series and we multiply it by a number, is it still converging? Yeah. It's a different number, right? So we have talked about this when we did properties and sequences, or series. Does anyone remember? I know we added and subtracted. Yeah, a constant, so it was here. It was like 5 days ago. After the test for divergence, we said that if you have two series and they're convergent, then so is a constant time the series. We did write it down. Right there. So y'all can believe in. Okay, awesome. So we can do this kind of thing where let's look at the series times 5/2. So this is converging or diverging, which one? Converging. So if we can show that this series is less than this one all the time, we also have convergent. We could take out the 5 halves just like we did before. This would be 2n plus 3/2. Right? So we're down to the question, is this bigger than this? And smaller. Just kidding. We want it to be smaller. Is it? Yeah, it is. So we have convergence. Now, if you were writing this out in a problem, you would need to write these things. We're kind of just talking through it. But you need to write that, you know, you can even think yourself through it by writing it out. So this, we're going to compare it to this series. We know that this series is convergent because it's a p series times a constant. So we need to figure out if this series is less than that one, kind of that thing. You can say it's convergent because it's a p series, or p is greater than 1. Because r is between -1 and 1. So yes, kind of, but does that make sense? Awesome. All right, ln k over k. You're back. Yes, I have. Why? Oh, only one of them. Sorry. I didn't hear what you said though. Tell me that I'm something. Oh. You know, we must not have the right class yet. That too. Okay. What does this remind you of? P series or geometric series? You can find it. It's right up here somewhere. Really? I'm not tricking you. Yeah, this is a p series where p is 1. Okay, so we're looking to compare this to 1 over k. Is this divergent or convergent? Divergent. Why? Because p is equal to 1. So now we are left to prove that ln k over k is bigger than 1 over k. Is that true? Yeah, how do you know? ln k is getting bigger, right? So it's going to be always bigger than 1. Or you could say, whoops, ln k is always bigger than 1 when k is bigger than 1. Therefore, ln k over k is bigger than 1 over k. I lied. Okay, ln 1, we're starting with 1. So this is a problem. I wrote this right, but we didn't talk about this. Okay. The very first term is going to be what? If we plug in 1. 0, which is actually smaller than 1 over k. But what about when we get to 2 or 3 or 4? We're good, right? After 1, we're good. It is? Look for it. No. But I've seen mine. Yeah. Okay, but Ellen K 1, 0. Oh, I get what you're saying. I don't know why. Okay. But here's the point. It's going to eventually be bigger than 1. At what point is it bigger than 1? We're looking for integer values. Ellen 3. So this goes back to So this goes back to you can add finite numbers of numbers together and it won't affect an infinite series conversion. Remember we talked about that? You can add as many numbers on at the beginning as you want. As long as when you get to the part where you're going to go to infinity, it converges. And you could add 50 billion numbers to the front and still converge because it's a finite number of numbers. So, what we would need to say is ln k is bigger than 1 when k is greater than 3. But through that statement, we're saying that it's eventually always bigger. Are you following? Okay. It's ultimately bigger than the other for an infinite number of terms. Are you done? Oh, okay. So yes, because of this, we can also say that ln k over k diverges. Okay, this one makes you think of a geometric series, right? In fact, the geometric series 1 over 2 to the n, which we just talked about, was convergent. However, if we, so these were my notes, so sometimes it's not very clear what I was going to say by reading it. Yeah, it's -1. So it's going to be bigger. Do you see that? Okay, so even though we feel like it's really close to 1 over 2 to the n, and 1 over 2 to the n converges, but it's just a little bit bigger, then we can use something called the limit comparison test. So sometimes if the order isn't correct, but it's close, one is bigger than the other, and we need it to be smaller, but it's close, then we should use the limit comparison test. Limit comparison test. So if we take the limit of these sequences, okay, let's say we have a sub n, that's what we're given on our paper or our homework or our test. And we know, like in this previous example, we had 1 over 2 to the n minus 1. That's the sequence that we're given. And we know that 1 over 2 to the n converges. If we take the limit of both and divide them, and we get a number, a positive number that's not 0, then we can say they either both converge or they both diverge. So I know this is a little bit confusing until you use it a few times. So in our example, 1 over 2 to the n minus 1 over 1 over 2 to the n, if we divide those and look at the limits, and we get a number, then they're both going to be what? Convergent or divergent? We know about one of them. So they both have to be convergent. Do you kind of follow? Maybe not. We'll do some examples. Okay. So back to this problem. We have the series that we're given. We have the series that we know is convergent. So we want to take the limit. I have no idea what this will look like. I'm going to move it down. Okay, I can work it out. The limit of 1 over 2 to the n minus 1 over 1 over 2 to the n. Divide them. Yeah, this is going to be 2n over 2n 2 to the n minus 1. Which I can, if I divide everything by 2 to the n, I get this limit here. So what's the limit? As n goes to infinity, this goes to what? 0, so it's just 1. So, since the limit is a number bigger than 0, we know that they both converge or both diverge. And which one is it? They both converge. Okay, are we good? Okay, let's do this example. It's 2n squared. Isn't that bad, y'all? What? I am right now. What are we going to do about all these snarky people next year? That's such a boring life. Okay. What does this kind of remind you of? Now this is where we have to think of in behavior. So we have to think of, calm down. The limit as x approaches infinity. This would look like 2n squared over n to the 5 halves, right? So first of all, test for divergence. Is it divergent? I mean, yeah. Test for divergence. Does it diverge? Can we say for sure? We can? We have n squared on the top and n to the 5 halves on the bottom. The bottom is bigger. So the sequence is going to 0, which is good. Okay. You said it's diverging. They're all laughing because they know you said divergent. All right. So this is what our sequence that we're going to compare this to will look like. 2n squared over n to the 5 halves. This is the one that we're using to compare. Not the one we have. This is the one we have. Now, this one is a p series where p is less than 1. What do we know about it? It diverges. So what we really want is for this one right here to be bigger than that one. But can we tell that it is? Not really. There's no really good, easy, like, oh yeah, I can look at that and just tell. So we need to use a limit comparison test. What? you say? Yeah, you're right. All right. We have the one we have times the reciprocal of the other. And go, do the algebra. I'm so confident in y'all right now. I showed you the answer. Okay. Okay, good. Good. If we multiply here, we get 2 into the 5 halves, 3 into the 3 halves divided by 2 root. Right, this is into the 5 halves, this is into the 5 halves. Right? 2 into the 5 halves over 2 into the 5 halves is going to be 1. Everyone follow? So what does it tell us? Divergent. Yeah, so it's horizontal asymptote. See, Maddie, the stuff doesn't go away. In behavior, horizontal asymptote. No. Bill is so smart. He's smart for him good. Okay, what page was it? 7, 8. We don't need the sum, which is awesome. Okay, do you think we can keep going? Actually, we'll get that note sheet out that we wrote all those things on. It's in your locker. A lot of good it's doing you there. Yeah. Does anyone have it, or am I spinning my wheels? Okay. Okay. We have comparison test is used if you have what's that hypothesis? Positive terms. You make it right there that you usually compare with a p-series or a geometric series. Then if you need to write something that helps you, like if a converging series is ultimately bigger than my series, a convergence of a diverging series is ultimately smaller than mine, it diverges. Did I say that right? If a converging series is ultimately greater than mine, it converges. If a diverging series is ultimately smaller than mine, it diverges. In your own words, or you can just rewrite what we wrote in the notes, just something so you have it there. And then make yourself a note that says something about if it can't be compared using, if it can't be determined that one is always bigger or smaller, use limit comparison test. And then write out what limit comparison test was. Are you good? How
I told you? I probably haven't. The mock test is the 18th, next Saturday, at 8 a.m. Probably in the library, but I haven't for sure got those plans arranged yet. It is optional. You don't have to be here, but if you're taking the AP test, which all you are, really like for you to be here if you can. If you have the option, please choose yes. If you're out of town or something, that's fine. No, it does not. So we will sit for the whole thing. So if you plan to leave like a little before noon, I'll bring donuts and juice. So it's incentive to be here in the morning. We're gonna start right at 8, so try to be here at 10:45. Okay? Huh? Oh, the ACT is also going on that day, so come in the circle doors. Got it? Y'all are all like blank staring today. No, like a week and a day. Okay. We're going to start the alternating series test. I'm not exactly sure how far we'll get into this, but we'll start it. Okay. It's easy to tell when you should use the alternating series test because it's alternate. The idea behind this is that if we have a positive number, negative number, positive number, negative number, positive number, negative number, and they're approaching 0, then the series will be convergent. So this is a really easy test. Did everyone see that? Look at me for a second. So if you have, here's 0, here's the axis. And you have a positive term, negative, positive, negative, positive, negative. See, if they're getting close to each other, if they're getting close to 0 and you add up all those, then you're going to be convergent. Make sense? So basically the test says, if you have an alternating series test, or an alternating series, and the second term is bigger than, smaller than the first term. So like I was showing you, it's getting closer to 0. They're farther, closer to the axis, not farther away. And the limit of the sequence is 0, then the series converges. Super easy. We'll talk about the sums. Probably not today, but. Okay. Looking at this alternating series, -1 to the n minus 1 over n. Now, on first thought, we're like, oh, wait a second, this is a p series, or p is 1, so this is divergent, this is bad. If we write out the terms, we have 1 minus a half plus a third minus a fourth. You see how that's getting smaller and smaller. It satisfies both conditions, right? Every additional term is bigger than the first. And the limit is 0, right? The limit of 1 over n is 0. So it converges by the alternating series test. What? What? The limit, because the limit is 1 over n. Notice that here when it's defined, you can't see it. The -1 to the n minus 1 is not included in the sequence. Do you see that? So when you're defining an alternating series, you just forget completely about the -1 to the n minus 1. All you have is whatever's left. When you look at this one, what's left? Just 1 over n. Is 1 over n plus 1, and I think I wrote this out, is 1 over n plus 1 is less than 1 over n. So every additional term is smaller than the previous term. So 1 over n is the limit as n approaches infinity is 0. That's what we care about. See? This one, basically you take away that -1 to the n minus 1 and you just test for divergence. But this time, we can use both. Doesn't converge. I know. It's pretty fascinating. It is true. No. Remember when we did integral test? and we did the integral of 1 over n. What is the integral of 1 over n? ln of n, which is doing what? Getting large. You add up all those getting bigger terms, it's just getting bigger. Don't calculate at me. All right, next example. -1 to the n. Actually, I'm super excited with our progress today. The last 2 days have been amazing. Y'all were amazing on the end. That's why that was amazing. Yeah. Yeah, that's funny. Okay. So we have is each additional term getting smaller? We can think of this as, look, we can think of this as 3/4 times -1 to the n over n minus 1/4. What's happening? We'll talk in a minute. We got to do this problem. We have to do this problem. Is it getting smaller? It's like 1 over 3/4. So we could really actually keep simplifying this. So n over 4n minus 1 over 4, which would be, is this, no, we're not getting anywhere, are we? 4n over 4n minus 1. No, I just multiplied by 4 over 4. Yes, you do. Okay, okay, all right, here we are. None of that went anywhere, and that's good. How are we going to tell if something is decreasing? In calculus, how did we learn to tell something is decreasing? If the derivative is negative. So let's real quick find the derivative. So we have bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. The bottom squared is always positive, so we don't care. The top is 12n minus 3 minus 12n. Oh! What? It is always negative, which means it's decreasing, so we're good. Number I is good. We got decreasing. So you may have to do that sometimes. Take the derivative. Okay, now, is the limit 0? Y'all are like so dense. What is the limit? What is the limit of this? 3/4, which is not 0, so it diverges. It's what? Okay, so even though we figured out that it was decreasing, which is good, that's a good point. You may have to use the derivative to confirm that it's decreasing. We figured out it diverged in the end anyway. Really sad day. All right, I will text you your homework. Yeah. Because I know how y'all are.